Today I want to tell you about some interesting results concerning contrast structures in one singularly perturbed problem with a weak reaction discontinuity. We consider this boundary value problem where epsilon is a small parameter, D is a simply connected region on the two-dimensional plane with a smooth boundary delta D. A, this is nonlinear function, is a two-dimensional vector function. N is an outward normal to the curve delta D. And let C0 be a simple smooth closed curve lying entirely in the domain D, which divides the domain into two parts, D minus bounded by the curve C0 and D plus bounded by curve C0 and delta D. Functions f and a are sufficiently smooth in their domain of definition, but the function f1 is discontinuous, so it is a weak discontinuity. It multiplied by epsilon. We assume the following conditions hold. The function f1 have the following form. Here the function f1 undergoes a discontinuity of the first kind, and the function f1 minus and f1 plus are sufficiently smooth function in the domains D minus closed and D plus closed. Condition A2. Let the degenerated equation has exactly three ordered solutions satisfying the inequalities. The last two equalities mean that the solutions phi plus minus are stable and the solution phi 0 is unstable. We investigate the solution to problem 1 such that it is close to the function phi minus in the domain phi minus and to the function phi plus in the domain D plus, while it changes abruptly in the neighborhood of the curve C0. We introduce the stretched variable psi equal to r over epsilon and consider the associated system for problem 1. Each of points phi plus minus 0 is a saddle point of the system 2 on a phase plane u wave v wave. Condition A3. We assume that for any theta, the separatrix issuing from the saddle phi minus 0 must enter the saddle phi plus 0 and can be represented in the parametric form. The dependence of this function on P is expressed by the equality u wave 0 is equal to P. P is interpreted like level the value of asymptotics between phi minus and phi plus on the curve C0. We construct the asymptotic approximation in the following form. Here is a regular part U with bar depending on x and epsilon, and q plus minus depending on psi, stretched variable, theta and epsilon. Theta is a parameter which varies along the curve. The functions q describe the solution in the neighborhood of the curve C0. and the functions R describe the solution in the neighborhood of the boundary delta D. Here we use stretched variable psi gamma. We're looking for the function P depending on theta epsilon in the following form. In order to determine coefficients Pi, we use C1 matching conditions. The difference between the derivatives u minus and u plus can be represented as follows. Here, L and K I are known functions. We can express them via the first coefficients of the task. It's very important that the coefficient L, its coefficient before the derivative, depends on the tangent to the curve C0 component of advection vector. Tangent component of advection vector A. We require the condition A4. Let the nonlinear first order equation 6 with periodic condition here has solution such that P0 lies between phi minus and phi plus on the curve C0. Periodic functions of higher order Pi can be determined from linear equations. We require the following solvability condition for these tasks. Let the following inequality holds. This coefficient L depends on tangent component of advection vector and cannot be equal to 0, as you see. To prove the existence of the solution, we use the theorems on differential inequalities from Pavlenka and Ulyanova work. It follows from the results of this work that the existence of the lower and upper solutions to problem 1 leads to the existence of the solution u epsilon to this problem that lies between these two. Here is the well-known definition of upper and lower solutions. The functions alpha and beta are called the lower and the upper solutions of problem 1. If for sufficiently small epsilon the inequalities hold. The ordering in D closed. The action of operator in equation 1. The condition on the boundaries and the derivatives condition. To construct these upper and lower solutions, we use the constructed asymptotics. And we modify it in the following way. We denote beta n plus 2 depending on x and epsilon, the upper solution of problem 1. Here, u n plus 2 delta is the function u n plus 2, where p is replaced by p delta to satisfy the inequality 1, this inequality of ordering, and to satisfy the inequality 4, the derivatives condition. Mu is a positive constant chosen so that inequalities 2 and 4 hold. 2, and 4. And the function q minus, depending on xi theta, are introduced to eliminate the discrepancies that arise in inequality 2 because of adding mu. And the function r beta is a function to prove inequalities 3. Thus, the theorems are proved. We suppose that conditions A1 from A1 to A6 hold. Then for a sufficiently small epsilon, there exists the function u depending on x and epsilon, which is the solution to the problem 1, such that the function un, our asymptotics, is the uniform asymptotic approximation for it. And the inequality 9 holds. Also, we have a stability theorem. Let conditions from A1 to A6 be satisfied, then the solution of problem 1 is asymptotically Lyapunov stable with a stability domain at least alpha 2, beta 2, and therefore U is the unique solution of problem 1 in this domain. Here is the example. We use the nonlinearity in the cubic polynomial form. This is critical case. We use the curve C0 in this form. This is circumference. Also, we choose the advection coefficient. This is a vector. For simplicity, we choose it so that tangent component of this vector is equal to 1, and normal component, which is called A, is equal to 0. The function f1 is chosen to satisfy necessary conditions. Here is the result. The numerical solution, this is dashed line, and zero order asymptotics, red line. This is three-dimensional picture of zero order asymptotic. It was established by the numerical experiment that this solution is asymptotically stable. Thank you for your attention. Have you any questions?
Молодец. Отлично. Хорошо, коллеги, вопрос, пожалуйста. Сергей Юрьевич, задайте сложный вопрос. А вот слышите? Ключ Андроид. Ну да, у него сбоку. Вот если даже он не может задать сложно.
Мы зададим вопрос позже, Николай Николаевич.
Не, я это слышу, просто я отключился, пока подключишься, тут целое дело.
Понятно. Нет, это так, я говорю. Ну, хорошо, хорошая работа, интересная.
Нет, хороший.
Новые продвижения, эффекты новые. Задача с балансом, где линейность, вот, многомерность проявляется по существу. Вот, задача с балансом и задача с конвекцией с определенной точки, без конвекции. Многомерность проявляется по существу. Вот в этой задаче как раз мы видим эту факту.
У меня тогда дурацкий вопрос, я по-русски спрошу. Может быть, я прослушал, а вот, так сказать, может вот этот вот фронт, он такой быть с особенностями? Ну, там, не гладкие какие-нибудь, еще что-то вот. Так-то он у вас там разбегается в виде, ну, похоже на окружность, да, там. А может там какие еще могут быть такие уголки?
Уголки будут...
Сергей Юрьевич, стационарная задача. Он не движется, он локализован в окрестности точки разрыва вот этого добавки мало.
Не, но сама просто кривая может быть не гладкая. Так сказать,
Она
да, вот
немножко
так
во
вот.
втором порядке. У нее сшиты первые производные, а вторые уже разрывные.
Нет, вот Сергей Юрьевич задает
Нет.
вопрос. Пожалуйста.
Не, я имею в виду, что, может быть, вот на этой вот окружности, да, которая тут изображена, вот, то значит, она может быть с уголками с какими-то. Вот.
Нет, очень интересно.
И бывают случаи часто, в общем, ну, в гиперболических задачах.
Задача с особенностями вот этих кривых пока не делать. Ни в каких задачах, в том числе в этом.
Прекрасно, спасибо. Еще
Вам спасибо, да. Thank you very much, да. Окей.